Welcome back to the second part of the fifth experiment on digital modulation. In this experiment, we will talk about frequency shift keying and phase shift keying. So let's start our discussion with frequency shift keying. I have already built the circuit of frequency shift keying. You already know the different components of this circuit from previous experiments. Let me just explain the function of this circuit. At first, I want to mention that we have already done the experiment for binary amplitude shift keying. So the method that we followed for binary amplitude shift keying will also be followed in this circuit as well. So let's start explaining. Okay, so this is our circuit for frequency shift keying. So this is our input source. We are using Bernoulli binary generator for producing the pulse. So our pulse is a digital pulse of 1 and 0. Let's say it's 1 0 1 0. So there are two paths where the input sequence is fed. The first path is this one. In this path there is a product modulator or simply a multiplier block. In this multiplier block there are two inputs. One input is obviously coming from the input source, and another input is coming from a sine wave of a particular frequency. This frequency is 20 Hertz. In this experiment, you can choose whatever frequency you want. So if it is 1010 and it is multiplied this sine wave, then when the input is 1, the output will be exactly like the sine wave, and when input is 0, then the output will be null or 0. So the output for 1010 will be something like this. So 1010. So for first one, we will get a complete sine wave. Then it will be null, then it will be another sine wave because it's 1 0 and 1 again, and then it will be 0 again. So it's 1 0 1 0. So this is the output of this modulator, and here there is a circuit. This part of the circuit is actually inverting this input sequence. I have already explained the function of this part. Let me explain that once again. Let's say there is a subtractor here. In this path there is 1 and it is fixed, and in this path we have a digital sequence as input. Let's say the input is 1, then 1 minus 1 is actually 0 in the output, and if the input is 0, 1 minus 0 is actually 1. So you can see if the input is 1, output is 0, and if the input is 0 and output is 1. So actually this circuit is inverting the input sequence. Here is the circuit that is inverting the input sequence. So if the input sequence is 1 0 1 0, the sequence here will be 0 1 0 1. This is another product modulator, and in this modulator there are two inputs. One is of course the inverted binary sequence, and another one is a different sine wave. The amplitude of this sine wave is exactly same as the previous. In both the cases the amplitude is 1, but the frequency here will be different. So here we'll use a low frequency. Let's say frequency is 10 Hertz. Let me erase this portion. Okay, so now the input is 0 1 0 1, and we have a frequency, we have a source of a frequency 10 Hertz. So when the input is 0, output will be null. So in this section it will be null. Then when the input is 1, we will have exactly this wave in the output. So now the frequency is 1 Hertz. So let's say this. So we have a sine wave, and then again it will be null for some time as it is 0 here. Then for the final one we will have another sine wave. So it is for 0 1 0. Now in this adder these two signals are added. So the output will be something like this. So sorry, let's just shrink the size of the output. So as you can see, here it is a sine wave and here it is null, so the output will be exactly this one. Here it is null and there is a sine wave here, so output will be this one. So it goes on and on. So for 1, the input sequence was 1 0 1 0. So for 1 we have a high frequency, for 0 we have a low frequency. The frequency that is used here will be reflected in the output signal for 1, and the frequency which is used here will be reflected in the output signal for 0. So that's all for frequency shifting. In the report section, you will need to demodulate the input signal, which is the modulated signal now, and you will need to retrieve this input sequence back. So this is the task for the report. So let's move on to phase shifting. So again, I have already developed a circuit for phase shifting. The idea is very similar, but now we will use the sine waves for different phases. When we were doing amplitude shifting, we were basically developing the same circuit. In that case, the amplitude of two sine sources were different. For the frequency shifting part, we were also using the same circuit, but now for two sine waves, the frequencies were different. Likewise, for the circuit of phase shifting, we will again use two different sine waves for two paths, and the frequency and amplitude of both the sine waves will be same. Only difference will be in phase. Let me show you. So this is the circuit, and I'm not going to explain this once again. Just I'm showing the attribute of it. So in this sine wave, we are having a phase of pi by 2. So this will be a cos wave because the phase shift is pi by 2. So and the frequency is 10 Hertz. Okay, amplitude is also 1. You can see. And in the inverted path, in this sine wave, you can see the amplitude is 1, so same as before. Frequency is also 10, same as before, but the phase is minus pi by 2, so it is actually a negative cos wave. So we will see a transition of the phase whenever the input is changed from 1 to 0. Let's do it for 10 seconds first. I'm simulating this one. It will take some time to simulate. Okay, so the simulation is almost done. We will now check the output in the scope. So it's taking a lot of time to simulate because I have chosen a very small sample time. So when you will choose a very small sample time, the simulation will take more time. Okay, so let me check the output. So here you can see it's not very evident. So let me just zoom it a bit. Let me zoom it for four cycles. Okay. Okay, here you can see when my input was high, I am having a cos wave. You can see it's a cos wave because it's starting from 1. Here there is a transition from 1 to 0, and you will see a definite sharp change of the wave. The ending of this wave was here. You can see it's clearly here. Let me zoom this so that you can. Here you can see the transition. It is the end of the sine wave or the cos wave for high input. When the input is becoming low, there is a sharp change and it is a minus cos wave now. How do we know this is a minus cos wave? Because minus cos wave starts from -1. You can see it's starting from -1. Again, when there will be a change from, let me just take it back to the original way. Okay, so let me just show another transition for better clarity. Okay, so in this transition, it is changing from 0 to 1. You can see this was low here and suddenly the input is high here. There is a sudden change in the output wave as well. You can see a negative cos wave here and suddenly the output is becoming a positive cos wave because now the phase shift is pi by 2 as we are having a high amplitude. So that's all for phase shift keying. In the frequency, in the report, you will need to demodulate this modulated signal and generate the output from it. You can do this by following the method that is shown in the theory lectures. So that's all for EEE 342 course. Hope you enjoyed the lab. Thank you.